Hey everyone, this is Jon Kakaley, and today we're going to be talking about solving the cocktail party problem with deep learning. This is it's not, I don't consider it a longer video. It is longer, but it's more complete. I posted a shorter video, the same subject, but because of time constraints, I had to go over some very complex concepts very quickly. So if you wanted a more in-depth explanation about how this experiment works and the principles behind it, this is the video. Also, a lot of the techniques I use are really state-of-the-art deep learning. I mean, this experiment wouldn't have been possible 6 years ago, so that's pretty cool. So anyways, we'll get right to it. What we're going to be talking about today, table of contents, quick overview of the cocktail party problem. And all we're trying to do is we have a mix of audio sources, and we want to separate it into the isolated original sources. Computers have a very difficult time doing it. So that's the problem that we're trying to solve today. And how we're going to do that, well, first we'll talk about the experiment and the goals. So we're going to limit our study to a two-person cocktail party problem. We're going to collect multiple samples of audio from two unique sources. One is going to be audio of myself reading various things. Another is going to be YouTube samples of a female TV anchor. We're going to develop a method to separate a blinded audio mix into its original sources, and then we're going to use deep learning techniques to train an AI network to recognize those patterns. And finally, once we have that AI network trained, we're going to take a collection of audio samples, mix them together, and see if the AI network that we trained is able to separate it into the original sources. We're going to measure the accuracy, and we're going to measure the time it takes to complete the processing and see if real-time processing and real-time separation of audio sources is feasible. So this experiment is based on an experiment that a guy named Simpson did in 2015. We are improving upon that experiment with the following methods. We're using 16 kilohertz audio data instead of 4 kilohertz. Much more audio fidelity in that. We're training multiple AI networks using various sampling techniques. In his experiment, he only used one. He used the soft mask technique in his experiment. I found a way to improve that technique with an iterative method. We're testing the AI network with truly blind audio samples. In his experiment, he only tested it with validation samples that technically the AI network had seen during training. So we're testing it with truly blind samples. We're going to measure the percent differences between the original waves and the reconstructed waves, and we're going to measure the time needed to reconstruct the samples. So we'll get right to how this whole thing works. So the first thing we want to do when we have an audio wave file is we want to perform what's called a short time Fourier transform on it. And what that is imagine a Fourier transform, but a tiny window that scans across the sound wave, performing Fourier transforms as it goes. And that produces what's called a spectrogram. And the reason we want to do that is because with a spectrogram, you can recognize the patterns in each voice easier. For example, notice in voice 1, in the high frequency range, there are many appearances there. You don't see that in voice 2. So when you look at the two that are mixed together, you can clearly see that, oh, this is from voice 2 and this is from voice 1. And an artificial intelligence network is going to be able to see that pattern and recognize it and perform separation based on it. So that's why we're doing this. Now, once you have things in a spectrogram format, you create what's called a soft mask. This is the MATLAB matrix math for it. All we're really doing is creating an inversion of the spectrogram. And if you look, you see, this little area here shows up right here. It's just an inverse. Once we create the soft mask, we take the mix of audio, the blind mix, we piecewise multiply it by the soft mask of the source that we wish to isolate and reconstruct, and the result of that is a spectrogram of the voice that we're looking to reconstruct, and then we just perform an inverse short-time Fourier transform on it, and we get a reconstructed version of the sound wave. Now, how does this work with AI? So essentially with AI, we're going to feed all of this stuff to an AI network during training, and it's going to learn to detect patterns so that when you input a audio mix, it will generate a soft mask of the voice that we wish to reconstruct. So that's how that's going to work, and this is what we're going to use for training. So training audio data, we're going to use about 5 minutes worth of training data of myself and a TV anchor named Brooke Baldwin. I don't have, I should say, just in this crazy time, that I have no, affiliation or liking or disliking of her in general. It's just who is the first person to pop on to YouTube in terms of data to extract. So we're going to use about 5 minutes of training audio data. We're going to use 8 seconds of audio data of myself to validate the training process. And it's very important that I point out that we need to normalize that data, meaning we smooth the sound waves out a little bit. We smooth the spectrograms out a little bit. And that allows the AI network to recognize those patterns better with smoother spectrograms. We also want to chop the spectrograms into small chunks of data. Again, that allows the AI network to perform better pattern recognition. So here's the training code. A lot of people get very intimidated by the words deep learning. It's really not as complicated as you might think. This was all the code. This is not the entire code for the program, but in terms of the actual creation and training of the deep learning network, this is it. This is all that it is. So you have the layers here, 12-layer deep learning network. You have the training options here. This executes the training sequence, and this uses the resultant network to predict the mask. So that training took about an hour. And this is just a chart of the loss and the error involved in the process. And these are and then we ran it through a set of 5 different tests, and each test had a different sample set of audio sources. And as you can see, the results were quite good. Sample set 2 is one of my favorites. And again, so you input this into the program, a mix of sounds, and the program is completely blind to the separated sources, and it outputs these reconstructed sound waves. These sound waves right here, these are the originals, and they're just here for comparison purposes. And look at how similar these. Look at the detail, the similarity in the detail. You see this detail here is almost the same. That detail is the same. That's the same. A little bit of difference right here, so you get a little bit of error. This here is a little different than there, but it's not bad. I did an error calculation. We're looking at about 3.5% error. Again, very similar results. Very similar in test 3 and 4. Test number 5, I wanted to point out here at the end. So here's maybe a little bit of a weakness in the method. So if you look at this, it's nearly perfectly reconstructed, but when it's supposed to be completely blank, it obviously pulled in a little bit of audio from voice 1. It's not terrible, and if you look, the amplitude, it actually suppressed the amplitude, so clearly it recognized that this was not supposed to be here. It just wasn't able to suppress it as much as it should have. So that's something that can be improved upon in future experiments. And real quickly, let me see if I can play. We'll go back a few slides to sample set 2. So this, I'm just going to play. So what I'm going to play is this wave right here, just so you can see what it's like.
Life is really simple, but we insist on making it complicated.
So I'm not sure how well that's going to pick up in terms of my MacBook Pro mic, but you should be able to make out my voice. And you can see that there's a little static that represents the errors, but you can clearly, I at least can clearly hear my voice on my end, so it works pretty well. Elapsed time, we processed 31 seconds of audio in 14 seconds on a 2020 MacBook Pro, and that is that's really good. That means that real-time wave reconstruction is definitely possible, and I would also take away that deep learning is an incredibly effective technique for this. Again, average error of 3.5%. Now, I will say something about that 3.5% number. That seems like a small amount, but with wave reconstruction, you really want to get it close to perfect. That number really needs to get down to like 0.1 or 0.05%. Think about it. If you're listening to your favorite song and there's 3.5% error, well, it's going to be choppy. There's going to be static in it. It's not good fidelity. It's not going to sound great. So to really get great sounding audio, you have to reduce that error even further. So more research really needs to be done on improving that accuracy. And I definitely have some great ideas for that, for those techniques in future research. And once you have the accuracy improved for a two-person cocktail party problem, then it makes sense to try to scale it up to solve potentially a 3, 4, 5, ideally infinite amount of cocktail uh, party problem sources. So uh, that's my presentation. Thank you very much for listening. And here are my citations. Thank you.